Okay guys, welcome to lecture 11. Okay, so today we're talking about that other famous quantum algorithm, which is Grover search. And we'll talk about a recent application of Grover search to something called approximate counting. On top of this week's lecture, we've got two quotes by someone who is, has nothing to do with quantum computing or even mathematics. They're by Beryl Markham, basically. Beryl was the first person, basically, to fly solo across the Atlantic. She went from Britain to North America. Okay, and she had a history of good writing and nice quotes. And, here are two that I think are well suited to Grover search. Basically, the first one says, the way to find a needle in a haystack is to sit down. Okay, so, the connection here to Grover search is that Grover search is all about finding a needle in a haystack. Of course, we're going to be a little bit more nuanced than sitting on the haystack. We'll be using quantum computation, but, that's what Grover search is about. And the other thing she said is that continuing a thought, she wrote after that, work and hope, but never hope more than you work. And this is also fitting for quantum search in the sense that, as we'll see, Grover search algorithm, gives us hope. In some sense, it allows us to do something better than brute force, but it's still not going to make things fully efficient. The worst case runtime of Grover search is still going to be exponential time. So in some sense, we still have to work more than we hope. Okay. So jumping to the intro of the course lecture notes for this week, basically, I like to think of Shor's and Grover's algorithm. They're kind of the two most famous exports of quantum computation in some sense, if you will. And they're kind of like two complementary famous soccer teammates, if you will, playing on a team. They each have very different roles, right? I mean, Shor's algorithm is kind of like the striker of the team, right? They are up front. They are very specialized. They have one job, right? And that job is to be very good at one thing, scoring, right? And on the other end of the team, you have the sweeper, right? And the sweeper's job is very broad, right? They're kind of their last line of defense, right? So whatever comes toward it, that person is supposed to stop the threat, okay? So they have a very general job. And so they have to be good at many things, basically. And Shor's algorithm versus Grover's algorithm is similar, right? Shor's algorithm is very efficient, right? It's polynomial time, but it only solves really kind of one class of problems, including the factoring problem, right? But Grover's algorithm, on the other hand, is very general. It's very broad, right? You can apply it to just about anything. But of course, the trade-off is that you cannot hope for a polynomial runtime in general now. So for example, kind of the canonical place where you might try and apply Grover's algorithm, which we'll talk more about shortly, is for NP-complete problems, right? You might apply it to something like 3-set, and there we'll see that we'll get a quadratic improvement over brute force for 3-set. Okay, so the outline for today's lecture will be, we'll first start by, of course, defining the unstructured search problem. And we'll talk about connections to 3-set and the exponential time hypothesis. Then we'll, talk about Grover's algorithm, and finally we'll show how to use Grover's algorithm in a recent approach for doing approximate counting. Okay, so let's start by defining the unstructured search problem. So this is section 2 in the notes, the unstructured search problem. Okay. So this is definition 1 in the notes. I'm just going to call it search for short. And the way this definition goes is as follows. As usual, we'll have an input and an output. The input is not given explicitly in some sense. We're assuming a very general setup, which is we're going to give you query access to some oracle, UF. And, here, what is f? Just like before for things like Deutsch's algorithm, f is going to be a Boolean function, which maps you from n bits to 1 bit. And it's unknown, of course, so we don't know what f is. And what do I mean by query access to this oracle? Well, remember, this just basically means, just like before, what we can do is we can compute. And when I say compute, what is the cost? We assume every time we access the oracle, we query it, it costs us 1 unit of computation. Okay, so we can compute the map xy goes to x and y XOR f of x. right? And remember that this is just bitwise XOR. Okay, so this is just the old definition we had for what it meant to have query access to an oracle, implementing a Boolean function f. Okay, and so this is the input. And what is the output? The output is find me an index, or an input basically, 0, 1 to the n, such that f of x is equal to 1. And this is, of course, assuming if such an index exists, right? And so in the most general setup, such an index might not exist. Okay, so you're giving me oracle access to this function f, basically, so I can apply the map f, and I'm searching for an input x, of which there are 2 to the n of them, right? I'm searching for an input that takes that input to 1. Okay, and so immediately, if you are very familiar with things like complexity theory, like NP or sharp P, which we'll talk about later, this looks a lot like something like circuit sat, or even just satisfiability, right? So you have, say, a Boolean formula, and you're looking for a satisfying assignment, right? And the key difference between things like sat and this definition of search is that we make no assumption that the oracle can be implemented efficiently on a classical computer. Okay, so in general, we're being extremely general. We have absolutely no assumption on the real under-the-hood efficiency of implementing UF. All I'm assuming here is that I have query access, input-output access to UF, that's it. And it costs me 1 unit of cost, right? I don't care how much it costs to actually implement UF. Okay, so of course what that means is that in Grover search, we will also be focusing primarily on query cost, right? The number of queries to UF I make. Okay. So that is search formalized. And let's just talk briefly about search in terms of its application to 3-sat. And something called, well, we'll discuss something called the exponential time hypothesis. Okay. Okay, so as we just sort of mentioned, I mean, this, when you first stare at this definition, it sort of reminds you of SAT, right? So indeed, if we want, of course, a special case of search where what is the function f? F is just some phi for phi a 3-sat formula. Okay, we can always plug that in. And of course, when phi is a 3-sat formula, then we can implement the oracle efficiently in that case on a classical computer, right? You'll give me your assignment x. I just evaluate the formula on x, right? And if I can do this classically, then I can do it coherently quantumly as well. Okay, and so what this means is that, later when we give the algorithm for Grover search, we'll see that this yields an order, brute force for SAT would of course require 2 to the n time. You have to try all the assignments. But we'll see that we'll get this runtime, right? And let me just be clear that this is just a half times n. This will be somewhat relevant now when we talk about the exponential time hypothesis for 3-sat. Okay, so a very naive application of Grover search. It's super general. You could plug in 3-sat and you can get a square root speed up over brute force, not over necessarily the best SAT algorithm, right? And so a natural question is, does this say anything about the complexity of 3-sat itself? Okay. And the answer is, maybe, maybe not. I don't think that's clear at this point, but I think it's worth taking a moment to compare it to something called the exponential time hypothesis, which in and of itself is worth seeing at least once in your kind of training, as it's played an influential role in areas like fine-grained complexity. Okay. So the answer is, okay, so maybe I should say, so it's generally believed that 3-sat cannot be solved in sub-exponential time, and I'll make this clear in a second what I mean by that, in sub-exponential time. Okay, so not only is it NP hard, but really something stronger, which is that you cannot hope to solve it in sub-exponential time. And for what I'm about to write, it'll be important for me to claim here without proof that, in fact, square root speed up for Grover is optimal. Okay, well, I shouldn't say maybe for Grover, but for the search problem, the best you can get over the brute force runtime of order n is order square root n. So Grover will never give you better than order square root 2 to the n, is what I'm trying to say. Okay? Or same for any quantum algorithm trying to solve the search problem. So there are lower bounds. We will not cover them in this lecture. Okay, so what does the exponential time hypothesis state? So this is claim 3 in the notes. Okay, or just ETH for short. Don't confuse this with, there's a similar thing called ETH in the quantum physics literature that has to do with thermalization. You know, these are totally different things. Okay, so depending on what your background is, don't get confused. And so let me be clear, this is by Impagliazzo and Paturi from 1999. That's where this statement comes from. And basically what it says is that there exists some constant epsilon greater than 0, such that any algorithm, any classical deterministic algorithm for 3-sat, so it requires at least 2, and here's my epsilon, n time on a deterministic Turing machine. Okay? So, you know, it's if you believe this hypothesis, which I think is fairly broadly believed, then you really believe that, you know, 3-sat should require at least, you know, 2 to the epsilon m time for some fixed epsilon, right? And, you know, this is why I bothered to write the runtime of Grover search with, you know, a fixed constant here. And so Grover's algorithm, of course, does not necessarily contradict ETH, because ETH doesn't tell us what this constant is, right? But there's a sense in which maybe it's not so surprising then that the best Grover search could give us is a factor of half, some constant here, right? If you believe the ETH, right? Because up to the ETH, you know, at least for a classical computer, you're not supposed to get better than something like 2 to the epsilon n. Okay, so that maybe puts the lower bound on solving search of, you know, this factor of a half in the exponent in a bit of context. Okay? And let's also just take a moment to talk about ETH, right, itself, just to give you some context about that. So is ETH itself true? Well, the answer is maybe, maybe not, right? Again, I think probably many people believe it is true. And what is nice about ETH is that if you believe it's true, then it turns out to give you very tight lower bounds, basically, right? I guess I shouldn't say very tight because tight is tight, lower bounds, for a number of problems in P, basically, right? So polynomial time algorithms, where, you know, the question is, can you do better than, say, the current best runtime of n cubed? Can you get it down to, say, n squared? Using ETH, or more accurately, a variant of ETH, one can show that, in fact, in some cases, you know, okay, order n cubed is the best runtime for this algorithm, for this problem in P. You can't get it down to order n squared, okay? And so assuming ETH implies, you know, matching lower bounds, and let me be clear, these are for problems in P, okay? These are polynomial time solvable problems, right? And the name of this area, this is something that's really kind of gained popularity over the last 5-10 years. So there was, for example, an entire thematic semester on this topic at the Simons Institute at Berkeley a few years ago, which you can look up, by the way, and all the Simons Institute talks are available free online, called Fine-Grained Complexity. Okay, so let me give you an example of this. An example is something called the orthogonal vectors problem, which I'll just abbreviate OV. And here what you do is you have an input as input. You're given 2 sets of Boolean vectors, so A and B, Okay, and what are they? They're just basically sets of d-dimensional vectors where the entries are just taken over from 0, 1, the set. So we're not over like a complex space or something like this. Okay, and basically you want to know, and let me be clear, the size of A, B can be assumed to be the same. So let me just call their size n. And the output is quite simple. Does there exist two vectors, v and a? So pick a vector from each set such that these vectors are orthogonal. Okay? So I give you two sets of vectors. Is there one from each set so that that pair is orthogonal? And exercise 4 in the notes, I mean, it's quite clear that you can solve this thing in time polynomial in the size of the sets, which is n, right? And the dimension of the vectors, which is d, right? Because you could just brute force try all pairs. So it's trivial, basically, to solve orthogonal vectors in order n squared d time, right? Try all possible pairs and then take inner products. The inner product costs whatever the dimension is, in this case d. And you might ask, is this the best polynomial runtime possible? Okay, it is polynomial time. And it turns out that if you assume a slightly stronger version of ETH, called the strong ETH, that will imply that order n squared d is the best possible. Okay. So if I'm not mistaken, don't quote me exactly on this, but the strong ETH, the main difference is that there you're not just thinking about, say, 3 sat, but you're thinking about k sat more generally, and as k gets bigger, it's believed that the exponent here approaches 1, basically. So do double check that, but that's vaguely what my memory remembers. Okay, so the point of this discussion, and by the way, there's a link in the lecture notes to a survey of Carl Bringman. If you're interested in things like fine-grained complexity, ETH, you should go read that. Follow the link in the lecture notes. So the point of this discussion, we defined the search problem. We kind of gave away that Grover's algorithm will give you a square root speed up over brute force. And it turns out that will be optimal for solving the search problem. And maybe that's not so surprising given the exponential time hypothesis, which says that since we can apply Grover search to SAT, we expect that you shouldn't be able to solve SAT, at least on a classical computer, better than 2 to the some constant times n, where Grover search solves it in 2 to the half times n. Okay? Okay. Good. So now let's talk about Grover's algorithm. Okay, so Grover's algorithm, I believe this dates to 96. So 2 years after Shor's algorithm. And for brevity, what I'm going to do is the search space is going to be n, right, which is 2 to n to the little n, which, little n is the number of qubits we have, right? So for us, efficient, as an aside, efficient for us should be poly n, right? The number of qubits, not poly capital N. So let's be clear. We're looking for something basically poly log of capital N. Okay, and so the claim will be we can solve search in order square root of capital N queries, basically. Okay, I don't want to say time because to give a full time estimate in terms of the total number of gates, you also have to take into account what it costs to implement that oracle, and we're not assuming any such thing for the oracle right now. So it kind of doesn't make sense to talk about time complexity unless you know what the oracle's cost is. Of course, later we'll see that the number of auxiliary gates, meaning the non-oracle gates, also scales essentially like order root n. Okay. Again, we're going to talk about the query model, right? We're just going to count the number of queries. Okay, so only cost is the number of queries. I don't care about how many auxiliary gates you're using in the process. And okay, the way I'm going to derive this is not the way it was originally phrased. Okay, I'm going to take kind of this popular viewpoint which came after the original discovery of Grover's algorithm, which is this geometric interpretation of Grover's algorithm. And in particular, what I want to do is I really kind of want to work from first principles and rederive the algorithm using this geometric viewpoint, right? How might you have come up with this kind of, if you thought about it long enough, if you're at the right place at the right time, how would you maybe have thought of this? Well, what do you know about quantum algorithms? Well, we know we've seen Deutsch's algorithm, which certainly came before Grover's algorithm. And there, you have this phase kickback trick. And so let's start with phase kickback, okay? And it turns out that by looking at phase kickback, not the way we used to, but in terms of a geometric viewpoint, it's going to kind of give away the right approach to take. Okay, it's kind of really nice how this will fall out. So let's remind ourselves what phase kickback was. Okay, so remember that this means applying the following, right? I don't apply my oracle to, remember I apply my oracle to an input x, right? But instead of setting the second register, the answer register, to 0, I instead put in the minus state, right? And what this did is that when I apply UF, this just gave me x and minus, so nothing changed, but I kicked out a phase which depended on the answer to x. Okay, that was the phase kickback trick. And in particular, I mean, notice how minus doesn't change here. It's just a one eigenvector of the unitary, basically, of the oracle, basically. So for the rest of this analysis, I'm just going to ignore this for now. Okay, so we'll just imagine that we can do the mapping. X goes to -1 to the f of x times x. Okay, because that's what it allows us to do. Okay, so we're encoding the answer in the phase. And now let's view this geometrically. Okay, and in the course notes, this is figure 1. And in figure 1, there are a few sub-figures, so I'll show you each one as we go. And so the way to kind of view this geometrically is we're going to work in a 2D space, basically. So of course, we're working in a very high-dimensional space in reality. We're working in, well, we've got n qubits, right? So we're in c to the 2 to the n, right? But it turns out that within that space, the entire algorithm won't touch most of that space. Actually, it's going to work completely in some two-dimensional subspace. Okay, so we can kind of project everything down to this two-dimensional subspace and just view the whole algorithm as taking place there. And the only question is, how do we define that two-dimensional subspace? Okay. A 2D subspace. And what I'm going to do is I'm going to write down the subspace, right? So first maybe I'll do this, right? So it's a 2D subspace, so it's spanned by 2 orthogonal vectors. And I'm going to call these vectors A and B. I haven't told you what those are yet. The question is, what should A and B be, right? What kind of 2D subspace will kind of tell me everything I need to know about the oracle, right? Well, the oracle, what does it do, right? It only cares about marked versus unmarked items. And these are all kind of classical in some sense, just strings, right? That's the only thing the oracle really understands. So a naive guess for 2 orthogonal states would be to say, let A correspond to a uniform superposition over marked items, and let B correspond to a uniform superposition over all unmarked items. Okay, that would be a naive guess. So let me just define A formally then. This means I'm going to define this as, here's a normalization, of course. Okay, sorry, let me just define these things first, right? So let A or B denote the set of marked or respectively unmarked items, right? And of course here we're talking about 0, 1 to the n. And what do I mean by marked or unmarked? Well, a marked item just means, f of x equals 1. Okay, that's just standard terminology in the field. Okay, so A is the set of good inputs that go to 1, and B is the set of bad inputs that go to 0, right? And so now, I can define a uniform superposition over A. So the normalization, of course, should scale with the size of A. And the sum over all elements x in A of x. Uniform superposition. And likewise, B is the uniform superposition over all elements which are in B, okay, which are hence disjoint from A. I mean, A and B are disjoint sets. Okay, that's what B is. And of course, so this is the, sorry, I've already written this, so that's what this is. That's what this is, right? And note, of course, that these two states are orthogonal, right? Because the set of marked and unmarked elements are, of course, disjoint. And so the x you see here and here, are going to be totally disjoint sets. So the inner product will be 0. So indeed, these guys will define a 2D subspace. They'll be orthogonal. Okay, so now the question is, I've defined this 2D subspace as a naive guess of what I should be looking at. What's the only tool right now I have at my disposal so far? Well, I just know about phase kickback, right? So how do I visualize phase kickback in this picture? So here's the question. What does phase kickback do in this 2D space? Okay, everything I do will be in this 2D space henceforth. So the answer is first given algebraically in exercise 6, or sorry, exercise 5, and it states that if I take UF to A, there's a question mark here, right? Let's see its action on these two states, right? I'm working in a 2D subspace, right? So if I want to know the action of the oracle in the subspace, then I just need to know its action on the basis states. This is, of course, assuming that UF will not take me out of this 2D span, right? So if it were true that UF were to map A to something that's not in the span of A and B, then this whole analysis would not work. Okay, but what I'm about to write down will show you that UF will preserve this 2D space. You'll always stay in this space. You'll never leave. Okay, this is why we can do the whole analysis in this space. Okay, so if you think about it, what does UF do? Well, on a marked element, right, here's UF. On a marked element, it just kicks out a -1 phase. On unmarked elements, it does nothing, right? So what is UF times A? Well, all the elements in A are marked. It's just an equal superposition, so it's just going to give them all a -1 phase, okay? And for B, they're all unmarked, so they pick up no phase, right? And so this is just going to leave B invariant. Good. So what does this mean? This means that, if I look at this picture, right, if I have some state, basically, let me pick a state here. So suppose I have some state psi in this picture. And suppose that had angle, whatever theta is, with B, right? So that state psi is the superposition of A and B. Then when I do phase estimation, what is it doing, right? Well, the component on the A axis, right, it's just hitting it with a negative. It's flipping it, right? The component on the B axis, this one, is unchanged. So in other words, what we're doing is we're reflecting about the B axis, right? We go from psi to some psi prime. Okay, so this is what you see in figure 1, the left side. So that is what phase kickback allows us to do in this picture. It allows us to reflect whatever state we have about the B axis, basically, about the X axis. Okay, good. So that's the first thing we learn. So that's good, right? Because what this means is that, the operation of phase kickback, let me again stress, that it keeps us in this 2D space. As long as my starting state psi is in this space, then when I play phase kickback, I stay in this picture. I don't leave this 2D picture. That's very important. So now the question is, if I want to play with this geometric picture, which start state psi to choose, right, in this 2D picture? Okay, and in particular, what does that mean? That means that we're in the span of A and B, right? Okay, so this is the next paragraph in the notes. So the start state. So which side do we choose? Well, all I know about this 2D space is I know A and I know B, right? Moreover, I have no idea, right, where, sorry, let me be clear, A and B are just equal superpositions over strings, basically, and together A and B, of course, give you the set of all strings. So this is worth noting, right? I'll make an aside here, note. So these guys are disjoint, right? And their union is a set of all strings, so basically they partition the space, right? So that's hint number one. Hint number two is that, of course, I have no idea where the marked elements are, so any position is as good a guess as any other. So the obvious thing you do, which is your first approach with any quantum algorithm, is you just prepare the equal superposition over all inputs, right? Because I don't know any better, right? So what we'll do is we'll choose psi just to be equal to 1 over square root capital N. Well, remember, capital N was 2 to the little n. Sum over all x and 0, 1 to the n of x. Okay, equal superposition. And now I'll leave it as an exercise to you to confirm that, in fact, what does this equal to? It is actually nothing other than, indeed, in the span of A and B. Okay, so it's in this 2D picture. And the coefficients in front are going to be square root, whatever the size of A is over n, plus, technically I could have written square root the size of B over n, but I'm going to just leave everything in terms of A. So I'll write it this way. Okay, the remaining amplitude. So if I sum and square these, I get 1, right? So I'll leave this as an exercise for you to confirm that this is indeed correct. So indeed, psi, this thing here, is going to be in the span of A and B. I just showed, here's the formula. And of course, this angle theta now that psi makes with B, right, is just going to be something you could work out now. Assuming you know what, the size of A is, of course, we don't know this, but this is just an abstract analysis, right? Then you could tell me exactly what that angle is. Okay, so that's exercise 8. Again, I'll leave this to you. All of these are fun ways for you to remember your high school trigonometry, basically. So for psi, as defined here, I mean, okay, the angle theta, okay, and again, by angle theta, I'm referring to, this angle up here, right, that angle theta, that thing is equal to the arc cos of square root 1 minus the size of A over n. Okay, so intuitively, right, if we just stare at this thing, right, if you look at the definition of psi, the more solutions you have, right, the larger your weight on A, right? That's what happens here. And so psi will be closer and closer to A. It'll be somewhere up here, right? And so the angle theta gets bigger. Whereas if you have a very small number of solutions, or marked items, then the weight on B is very large, and so the angle theta gets small. Okay, so that's the intuition. Good. So that's the setup. This is everything we know how to do so far, right? I know what phase kickback looks like. It's a reflection. And I have an extremely naive choice of start state that lies in the same 2D picture. So far, so good. So now let's remind ourselves, what is our goal, right? So what is our goal? My start state is psi, right? And what I want to do, ideally, is, if only I could take psi and rotate it counterclockwise in this picture, right? To bring it basically close to A, right? Ideally, you take psi and map it directly onto A. And then, of course, if I've prepared A or something close to A, when I measure A, what is it? It's just a superposition over all marked items. So I'm guaranteed to get a marked item, basically. Okay, so if only I could do this counterclockwise rotation, I would be done. Now, of course, the problem is I don't know the angle theta ahead of time, but at least in principle, there is a unitary which does this rotation, right? I mean, it's just a rotation of vectors. It preserves norms and inner products. So certainly there's a unitary that does this. The only question is, can I implement this unitary efficiently, meaning in time polynomial and little n? Okay, so here's the question now. Can we rotate the start state psi up to A using polylog n, right? Capital N, queries to UF, right? Again, we're working in query complexity. That's our goal. Can we do this? Okay. And you know the saying, 2 wrongs make a right? 2 reflections make a rotation. Okay, so another famous saying, right, in English is beggars can't be choosers, right? I mean, if you don't have many options at your disposal, you have to make do with what you have, right? And indeed, if our goal is to rotate counterclockwise to A, the fact that search is such a general problem, right? I really know next to nothing, right? I just have Oracle access to this, very general U. I really have very little at my disposal in terms of tools, right? The only other thing I know how to do is I can call the Oracle. That's it, right? I can prepare my start state psi, and I can call the Oracle. Sorry, but the one I want to focus on is not calling the Oracle, but in fact I want to focus on the other tool I have is I can prepare psi. Said that in the wrong order, clearly. Okay, good. So the only tools I have at my disposal are calling the Oracle. That was the phase kickback trick, which did the first reflection. But we can also prepare psi. Okay, so the only other tool, sorry, I should say, the only tools we have are number one, call the Oracle, and this allowed us to reflect about B. Okay, that's what we already saw in the phase kickback part. And the other thing we can do, as we just saw, is we can prepare the start state psi. And as exercise 9 asks you to do, since we can prepare psi, we can actually reflect about psi. Okay, so the ability to prepare psi allows us to reflect about psi. Okay, this is a claim I'm going to make. I'll give you some intuition as to why that's true, but I'll let you work out the details, right? And what is remember in a previous lecture we saw that for a rotation, for a reflection about a vector psi, the unitary is written like this. Okay? So in other words, remember this meant that u psi of psi goes to state itself, because reflecting a state about itself does nothing. Everything that's orthogonal to psi, however, gets hit with a minus sign. Okay, that's what it meant to have a reflection. Okay, so this is the claim of exercise 9. Again, I will not, let's go back up to show this picture. I'm not going to show you the full thing, but let me give you a sense of why this is true, right? So I want to reflect about psi now, right? So maybe I should actually just draw the next picture. First, let me show you what this buys us, and then we'll talk about implementation. So let me redraw that picture. Here's my A, marked items, unmarked items, start state psi, angle theta. Okay, this is what happened when we did, this was calling the Oracle, right? That allows us to do that reflection. And now what I want is I want to reflect about psi, right? So if I take psi prime and I reflect it now about psi, then I'll get this state, right? And now what is the angle between, let me call this psi double prime. What is the angle between my start state psi and this new state psi double prime? Well, that's 2 theta, right? Because, the initial angle here was 2 theta, right? And then I reflected about psi, so I get 2 theta up here. So that's, to be clear, that's this angle over here. So in other words, every time I make a pair of reflections, even though individually they seem kind of useless, when I put them together, right, 2 wrongs make a right. Now I'm able to do a rotation counterclockwise by the angle 2 theta. Whatever theta is, right? I don't know theta offhand. Remember, theta depends on the number of solutions, which I don't know offhand. Okay, but geometrically, this is what we are able to do. We are able to effect a rotation of 2 theta radians going counterclockwise every time I first do a call to the Oracle, followed by a reflection about psi. Okay, so in other words, so each time we applying what? If we first call the Oracle, which remember allowed us to do this reflection. So this is call UF. And I follow that with reflecting about psi. And for this, we're going to use the state preparation of psi in this exercise 9, right? And, the name I'll give to this is, it's a rotation about psi followed by, well, first a rotation about b, I should say, followed by a rotation about psi. And this is often called, this pair of operators is often called the Grover iterate. Okay, because you're going to iterate this over and over again. Okay, so every time I apply the Grover iterate, it rotates us counterclockwise by 2 theta in this 2D picture. Okay, that's wonderful news, right? Because I can just repeat this over and over again until I get close enough to A. So let me just very briefly kind of sketch how you would reflect about psi, right? And this uses a trick I once learned in graphics as an undergrad student. So I like to present it the graphics approach, which is that in graphics you often want to do all sorts of operations, right? Obviously geometric operations. You have some sort of figure, and maybe you want to do say a reflection or a rotation or something of that figure, right? And one way to do this is, of course, is that whatever kind of your current axes are, like your axes could be tilted, right? So maybe your axes look like this. I mean, you could always update your formulas for rotation and reflection to work with the new axes. You could do that, right? But that's not as systematic as we would like in some sense. An easier way to do it in some sense is you first take your rotated axes and you unrotate them. You take your axes and you rotate them back to the standard XY axis. And then you apply a fixed kind of rotation formula for this axis, which is always the same because the axes are fixed. So then you do your rotation in this space. And then, to affect really the rotation you wanted, you undo the change of basis. You go back to your rotated axes. Okay, and so that's how you do this kind of thing in graphics, and you can do a very similar idea here. If I want to reflect about psi, what I first do is derotate or unrotate. Basically, I undo the state preparation for psi. So this is kind of the sketch of how it works. To reflect about psi, right, number one, we undo the state preparation. So what I mean by that more formally is that if there was some unitary u such that if I applied to 0 to the n it gave me psi, then that means that what I want to do is I want to apply u dagger. Right? That's what I mean by this step. So apply u dagger, the inverse of whatever that preparation procedure was. Okay, so that will take psi back down to the all zero state. Right? So then if I had psi, it's going to map it back down to the all zero state. Right? And now I need to be a little bit careful, of course, because you'll notice that the all zero state is not necessarily in the span of these two. Right? At least I think that's true. But certainly the all zero state is not necessarily B, right? So it's a bit misleading for me to draw it the way I have. But nevertheless, it's going to rotate you to some standard bases like all zeros. And then it's not so difficult. So this is the part you really kind of have to think about, is to reflect about the all zero state. Okay, that's not so difficult. Okay, so I'll leave that to you as an exercise. So, i.e. I want you to implement 2, 0, 0 to the n minus identity. Okay, that's, this reflection about 0 to the n. And once you reflect in kind of like this fixed standard basis 0, and you just undo, so you redo the state preparation. Meaning apply this u, right, which is the same one for the state preparation. Okay. So again, you go back to some standard basis you know how to do things in, such as a reflection about the x-axis, the 0 state, and then you undo that rotation. Good, so that's a nice exercise. I'll leave that to you. And the moral of the story is, again, by taking turns, first calling the oracle, well, first we prepare our state, right? Okay, let me just write the algorithm down, actually, because it's time to do that anyway, rather than repeat myself 3 times. There we go. So let's focus on the number of iterations required, and for that I'll write down the algorithm. So here's Grover's algorithm. Number one, we're going to prepare the start state psi. And remember, that's easy to do because it's just all zeros and Hadamard's, right? That's easy. Number two, we're going to apply the Grover iterate, which remember is just this pair of reflections. First RB, oracle call, followed by R psi, reflect about the start state. And we're going to do it some number capital K times, right? I mean, I haven't picked K yet. And once you're done, you know, this is going to rotate you counterclockwise a certain number of times. Then you just measure your current state in the standard basis to obtain some input 0, 1 to the n, and you cross your fingers and hope that this is going to evaluate to 1 under f, meaning you've solved the search problem. Okay, so that's the basic algorithm. And there are two cases, right? So if there are no solutions or no marked items, what does the algorithm do? Well, you know, it doesn't matter how many times I rotate, basically, there are no marked items. So when I measure x, of course, I'm going to find an x which goes to f of x equals 0. It's the only possible answer, right? Always outputs x such that f of x equals 0. Okay, it's the only possible answer. Okay, so if on the other hand, case 2, so if the size of A is strictly larger than 0, then there are some solutions, right? What we ask is, you know, what should K be? Okay, and so K is this guy here, right? Over here, K up here. K is the number of times we apply the Grover iterate, right? How many times should we do this rotation? Okay, and so this depends, of course, on a number of things. Like, of course, it depends on theta, which we don't know offhand, but at least a priori to do the rotation, we don't need to know theta, right? We just need to be able to call the oracle. And it also depends on how close we want to get to A, right? I mean, in practice, you don't actually have to hit A exactly, although it's technically possible to do that. We won't discuss that here. But, you know, as long as you're close enough to A, when you measure, you'll still extract a satisfying assignment with high probability, right? So let's say we want to get to a point where, you know, the state psi double prime, or, you know, whatever, after I do sufficiently many rotations, I'm going to be close enough to A so that when I measure, I'll get a marked element with probability at least some fixed constant like a half. Okay, so how many rotations do I need to do to get to that state? Okay, so suppose we wish to succeed, and by succeed I mean, of course, once I measure my final state in step 3 of this algorithm, I want to get a satisfying x. So with probability at least p equals to a half. Oh, sorry, maybe I shouldn't write it that way. P is at least a half. Okay. Okay. So that's our goal. And what did I want to say? Okay, so now I'm going to draw the third figure, basically. Let's depict this now before we move forward. All right, graphically or geometrically, more accurately. So here again, I have B, same picture so far, A, right? I started at my start state psi, here it is, and this had angle theta over here with B. And after I run this thing K times, right, I'm going to end up at some state K. Well, let me call it psi K. Okay, that's what I get after doing K times the Grover iterate. And now you can argue that, you know, let's see how close do I have to be to A first. First, this is something we should figure out. How close do we have to be to A so that when I measure, I'll get a marked item with probability at least a half. So it turns out that, you know, if I kind of draw this cone, right, this distance basically, let's call it eta, right? This is exercise, sorry, I didn't get the right. By exercise. Okay, so by exercise 10, by exercise 10, it suffices for eta, basically this angle, to be in the range minus pi over 4 to pi over 4. Okay, so by which I mean I'm trying to account, sorry, this is slightly misleading notation. I really am thinking of eta as being a rotation in this direction, and so minus a negative rotation would go in this direction, right? So basically the size of this full cone here should be pi over 2, right? That's each of these is pi over 4 in length. Okay, so I'll let you work that out. That's exercise 10 in the notes. You're just going to have to remember some old high school formulas for angles between vectors. Okay, so that's kind of our target. We want to rotate till we're within pi over 4. So basically, you can think of this as being pi over 4. This is pi over 4. We want to rotate till we're that close to the vector 8. And the other thing we could figure out is, well, what is theta, right? In terms of the number of solutions. Let's be a little bit more precise. Okay, and so what I'm going to assume here, without loss of generality, so number 1, there's one thing I have to do. Number 2, without loss of generality, we can assume that the number of solutions, or the fraction of solutions, is at most kind of a half of the entire search space. Okay, there are various reasons you can assume this without loss of generality. I'm going to pick the simplest one, which I think is just very elegant, right? Which is that if there's more than a constant, more generally you can pick any constant fraction, right? But if more than half the solutions were, more than half the strings x were solutions or satisfying assignments, you could just pick one at random, right? And you just repeat this a constant number of times, or a log number of times, let's say, and you will get extremely high success probability, right? So you don't need a quantum algorithm then. So this is without loss of generality. We can assume that we have a small number of satisfying assignments. Okay, and exercise 9, based on this, will allow us to conclude that the starting angle theta is also at most pi over 4. Okay, it's not the exact value, but it gives me a bound over here. Theta is at most pi over 4. Okay, so I start with a small angle, right? So it's at most pi over 4. And I'm trying to fall into this cone, which altogether has pi over 2 in width. Okay. So this leads to exercise 11, which is that I'm not going to prove this, but just think about it a little bit. If I'm starting by with pi over 4 here, right? At most pi over 4, every time I do one of the Grover iterates, it rotates me counterclockwise, right? So every time I do a Grover iterate, it rotates me counterclockwise by 2 theta, which is at most pi over 2, right? So we're going, counterclockwise by pi over 2 radians at most each time. And since you see that, this cone is pi over 2 in width, right? We'll never overshoot this target cone, right? We'll never have to we'll never be, let's say, here and then make a huge jump and pass the cone and then have to wrap around and repeat this, right? We'll always land within the cone without needing to go around the circle. That's just going to simplify the analysis, right? So that's why we made these assumptions that, the number of solutions is small and so forth. Okay, so then what you could do is once you have all these facts, you can argue that you'll never need to kind of wrap around the circle. And so now it's just basic trigonometry to figure out that, I start here, I'm going to repeat this until I'm sufficiently close to this guy. So, how many times do I have to repeat that iteration? So exercise 12 says that you can show that it suffices basically to set k equal to the ceiling of 1 over 2 theta arc cos of square root of a over n minus pi over 4. And this is, again, to fall within gamma radians of a, right? And that meant that we could succeed with probability at least a half. Okay? And this is, of course, assuming that there are solutions, right? Obviously, otherwise you always succeed at probably 0. Okay? So this is kind of the basic thing you can come up with. And, if you want this is maybe somewhat unsatisfactory, of course, because, it also, this is basically encoding how many times we have to call the oracle, right? That's the number of times the Grover iterator is called. And, that depends on theta. And ideally, of course, we don't want our final query cost should have nothing to do with theta, right? It should just have to do with the search space size n, capital N, and potentially also the number of solutions, right? You might expect that as the number of solutions goes up, the cost of the algorithm should go down, okay? And so what you can do in exercise 13 is you can give a bound that only depends on a and n. And what you're going to do is you're going to show that sine theta is equal to, so again, we want to get rid of this theta, right? So the sine of theta is going to be something that just depends on a and n, okay? And, you're also going to need this fact, which I encourage you to show. Okay, so if your angle is sufficiently small, then theta is always larger than its sine. And then using these, via these guys, what you can show is that k is upper bounded by the ceiling of pi over 8 times the square root of n over the size of 8, the number of solutions. Okay, so in other words, to make a long story short, the number of queries we need for Grover's algorithm is nothing other than square root n in the worst case, and if the number of solutions is larger, then the cost drops proportionally. Okay, and again, let me be clear, this suffices to succeed with probability at least a half. And of course, once we succeed with a constant probability, we just repeat this thing a couple of times, and that will drive down the success probability exponentially. I mean, the failure probability exponentially. Good. So that's it. A nice exercise. So let me be clear. So this is Grover's algorithm. Okay. After numerous developments in terms of how to view the algorithm, now we have this very nice, for example, geometric viewpoint. And the algorithm is very nice and elegant in retrospect. One thing you could do as an exercise 14, is how many auxiliary gates are needed, meaning that if you start thinking more about beyond just oracle or query complexity, how many gates do you need, quantum gates beyond that, right? So you can think about that, and of course that will depend on the precise procedure you used for doing the reflection and so forth. The reflection about your start state. Okay, and so that basically closes our discussion of Grover's algorithm. The only thing is that you'll notice how to figure out the number of rotations I need to make, right, I kind of need to know theta, right? And well, knowing theta is kind of equivalent to knowing what A is in some sense. So, in many applications, you might know A ahead of time. Like maybe for example, that, there's a very small number, a constant number of solutions, say like one or a couple more, right? And then you could more or less just kind of assume there's one solution, and then this should more or less work as you expect, right? Then you'll know kind of how many rotations to make, because again, this is an order notation here. But more generally, of course, maybe you don't know the number of solutions, right? And so you might want an estimate of A to kickstart the algorithm, basically. And it turns out that you can do this amazingly, right? So not only can you use quantum algorithms to find a marked element, right? But you can actually use it to estimate up to a multiplicative error, which we'll formalize shortly. What is the size of A to begin with? Okay, let's see how long we've gone. Okay, it's been about an hour. Good. And that takes us to approximate counting. Okay, so what is approximate counting about, or what is counting about, right? So remember that search asked, given access to this oracle UF, does there exist an x such that f of x equals 1? Okay, so you're only trying to find one satisfying assignment. And, informally, counting just means, again, given UF, what is the number of x such that f of x equals 1? Okay. So this is, of course, a much more difficult problem, right? And to give you a kind of a feeling of how much more difficult it is, I think it's worth making a detour now in section 4.1 into a brief history of just counting in general. Okay, I'm not talking about grade school counting where you count on your fingers. I mean, counting from the perspective of complexity theory. Okay, so remember that to talk about to place this in the context of, counting theory, like classes like Sharp P, let's recall that in the plain vanilla definition of search, there were no assumptions on the actual complexity of implementing the oracle, right? We tried to make this as general as as general as possible of a problem. Okay, but of course, we live on Earth, and on Earth, physics tells us that we have to do things in polynomial time. Otherwise, it's more or less kind of useless for us. So, and even polynomial time can be a stretch in practice. Of course, in practice, you typically want linear or linear up to log factors, right, in order for something to really be efficient. So, typically what we want is for the oracle to have an efficient implementation. Okay. So, for example, sorry, let me not write it that way. So in reality, okay, we want UF to have an efficient, well, let me be a little bit more precise. Let's say I just want the function f to have an efficient, even a classical. So for our discussion here, let me just assume the implementation is classical implementation. And once you can do this, then you could implement the oracle UF quantumly, coherently. Okay, what do I mean by that? That would basically mean, for example, via deterministic Turing machine. Okay, polynomial time. Okay, so if we assume that, the oracle can be implemented classically, deterministically in polynomial time, then in that case, search, in this case, let me be clear, so this is not in general, in this case, is going to be NP complete. Right? It's certainly in NP, because you just tell me which string is going to be satisfying, and now I can evaluate the oracle myself, like in polynomial time, right? Okay, and why is it NP hard? Well, like we said, you can embed, in search, you can embed the case of the oracle being a SAT formula, right? So remember that we can choosing f equals to a 3-sat formula makes search NP hard, right? Then you're just really asking, give me a satisfying assignment to this Boolean formula. Good. So now, of course, we want to ask, we're talking about counting. So again, we're still talking about this scenario where f has an efficient implementation, right? Okay, so what if we ask how many x such that f of x equals 1? Okay. And when we do this, the complexity class we get is not NP anymore, right? So when we were just talking about search in this case of an efficiently implementable f, our complexity was exactly NP. But now if I want to count, now what we get is a class called Sharp P. Essentially by definition, right? You have some function that's efficiently implementable. You want to count the number of accepting paths of this non-deterministic Turing machine. And just to give you a sense of the difficulty of these guys, like the comparative difficulty of, let's say, search versus the counting version now. Well, NP, right, which is basically what search is going to fall into, is in basically something called the first level of the polynomial time hierarchy, which maybe after NP is the second most popular kind of verification class in some sense. Okay, so NP is basically quite low well, by definition, it's not in the first level, it is the first level, okay, of that hierarchy. And in contrast, the entire hierarchy, all the levels, all presumably infinitely many of them, right, is So entire pH is contained in p to the sharp p. Okay, so there's your sharp p, this is your NP over here. Okay, so in other words, if you had access to an oracle for sharp p to be able, if you could count, basically, you could solve NP and a whole lot more. Okay, it's a lot harder of a problem. Okay. Good. So as long as the function f is efficiently implementable on a classical Turing machine, deterministically, we're talking about basically sharp p is the class of counting problems. And so let's try and understand what Grover's algorithm or quantum approximate counting more generally is going to buy us in the context of sharp p. Okay, so that we compare kind of what we can do classically for sharp p problems versus, let's say, quantumly. Okay, so I'm still going to be talking about efficiently implementable f, so I'm going to keep drawing arrows under here. So let m equal to the number of x, right, such that f of x is equal to 1. So our goal is going to be to figure out what m is, right? So classically, there's kind of a very... Okay, so I'm going to use the word classically twice, or classic twice, but in the classical computation regime, there's a classic algorithm that's due to Stockmeier. Okay, Okay, Stockmeier's algorithm basically allows us to estimate m, to approximate m. Okay, so approximates m to within, well, it can't do it exactly. Doing it exactly is sharply hard. So it does it within a multiplicative factor of 2. So it'll get, whatever answer it gets will be within kind of 2 times the right answer. We'll be a little bit more formal later when we define quantum approximate counting. Okay, so you can approximate within a multiplicative factor of 2. There are 2 points I need to make here. Number one is that, the exact value of 2 is not so important here. You can actually boost this to, I think it's 1 minus 1 over poly, right? So you can really boost this to much better than 2 if you like. That's not the point. The other really important fact is you can't do this in polynomial time. Okay, and I'll state why in a second. So doing this, well, okay, let me not say that. So assuming you have access to an NP oracle. Okay. So more formally, the algorithm falls into a class known as BPP to the NP. So you have a randomized Turing machine basically that has access to this NP oracle. And, assuming you have access to this NP oracle, you can do this approximation of m to within a good multiplicative factor 2, which can then be boosted to 1 minus 1 over poly. Okay, so that's kind of the classic result classically. Okay, so in the quantum setting, right? So now quantumly, what do we get here? And we're using quantum approximate counting. So there's going to be a trade-off here, right? The trade-off is going to be no NP oracle. So unlike Stockmeier's algorithm, we're not going to use an NP oracle anymore, which is good, right? But, of course, if I give up the NP oracle, I can't, I'll state why in a second, but we can't make this thing work basically in polynomial time anymore. We're going to have worst case exponential time. Okay, so, but with worst case exponential time. Okay, so roughly speaking, it'll scale like the number, oops, other way around. There's a typo in the notes, I gotta fix that. N over m, right? So remember, capital N is 2 to the power little n, and 2 to the power little n is our input size. Okay, and this is, if you want, with constant probability of success. Okay, just to be clear. Okay, so you give up the oracle, but now in the worst case, your algorithm takes exponential time. And let me be clear that there's a sense in which you don't expect to get away from this trade-off, right? Like if you lose the NP oracle, you don't expect to suddenly be able to do things very quickly, even with a quantum computer, because approximating something called the permanent of a matrix, and this dates back to Valian's original paper on Sharp P and Sharp P complete problems, basically. The permanent is basically some function of the matrix that is very closely related to the determinant of a matrix, but funnily enough, oddly enough, even though the determinant can be computed in polynomial time, the permanent is very, very hard. It's Sharp P hard to compute exactly. And not only that, it turns out to be Sharp P hard to compute even approximately. Approximately within constant multiplicative error. Okay, so one source for this is this paper I've linked here, Aronson-Arkhipov, which is the this famous so-called boson sampling quantum supremacy paper from 2011. So where they explicitly prove this. Okay, so there's a sense in which you can't really have the best of both worlds, right? Either you're going to have an NP oracle, or you're going to settle for a worst case exponential time, because in general, approximating Sharp P hard functions within a constant multiplicative error is still going to be Sharp P hard. Okay, good. So that gives us a little bit about the context of, and by the way, of course, I hope it's clear from my comments that generally we don't believe that quantum computers can solve NP hard problems, at least not nowadays. So certainly we don't expect them to solve Sharp P hard problems, which are much more difficult. Okay, good. So let's now talk about quantum approximate counting via Grover search. Okay, so for clarity now, we were just talking about Sharp P, and we were talking about assuming that the function f in the oracle is efficiently implementable. But so now we're going to step back to our original setting where we assume nothing about the oracle. Okay, and so we'll define M as we did before, but let's just formally write down the definition now. It's a set of all n-bit strings, right, which take f to 1. And the goal now is to approximate M, okay, up to multiplicative error. And there's been kind of a classical approach for doing this for, I think, around 2 decades now, right? Which is that what you could do, kind of the classic approach, is you can run phase estimation on the Grover iterate, believe it or not. Okay, and it turns out that if you look at that iterate closely, the eigenvalues of the iterate encode the number of solutions. So then it's just a matter of how, to what accuracy you're able to run phase estimation. But of course, that has this funny overhead of requiring something quite complicated, which is, the Fourier transform. We don't want to do that, right? Ideally, it would be nice if, since we're solving a generalization of Grover search, wouldn't it be nice if you could actually just solve everything using Grover search, right? And that's exactly what we'll cover today. Okay, it's a very recent paper, which was published just this year by Aronson and Rawl, basically, and it shows how to solve, let me make sure I got the spelling right, good. It shows how to solve the approximate counting problem using nothing other than Grover search, okay? And, I should be really clear here, you can get quite a lot of mileage out of using Grover search as a black box. Okay, so here we'll see how to do approximate counting. Another kind of recent area of research that has used Grover search as a black box is the study of so-called quantum dynamic programs, or you're basically coming up with quantum algorithms that do better than existing classical dynamic programs at NP hard problems. Okay, so of course everything is still exponential time, but you're able to get like the actual runtime down asymptotically, okay, quantumly. Okay, so let me start with the intuition, because the intuition is kind of the naive thing you would try, but of course to make it work takes some careful manipulating. So what's the basic idea? Okay, so the basic idea is just this, right? Suppose, forget about everything about quantum. Suppose that, you want to know how many solutions there are, and so you let p, be the fraction of, p is the fraction of solutions, right? M over n. So in other words, every time I pick a random input, uniformly random, and I plug it into f, right? With probability p, I'm going to find a satisfying assignment, right? So the most naive way to find a satisfying assignment is, well, you just keep sampling uniformly at random, right? With replacement. And what that means is that if you repeat this over and over again and you kind of wait, how long will it take, basically on average, until you see a marked element? How many trials do you have to do? Well, typically you have to do order 1 over p, right? Which is order n over m trials of random sampling. Okay, until you see your first success. And the first exercise here, basic exercise 15, asks you to basically formalize this, right? Using something called a geometric distribution to formalize this entire random sampling experiment and try and understand, what is the probability that you deviate in terms of the number of trials from this expectation value before you hit your first success. Okay, so I won't cover that here, but that's a nice exercise. It gets you to learn about geometric distributions and also to apply Chebyshev's inequality. Okay, so I encourage you to do that. So this is kind of the naive way you try and solve this problem. Classically, you just kind of naively, what you might do is you keep sampling until you hit your first success, and then you invert that basically to get, well, you invert that, I guess, and you multiply by through by n, the total number of terms, to get the you invert and multiply by n exactly to get the rough number of marked elements m. Okay, and if you want to be even more precise, of course, what you do is you kind of keep going, not just until you hit the very first successful item, but you keep going until, really a constant fraction of the items you're seeing is going to be, wait, do I want to say that? Maybe I'll leave that for the algorithm a bit later. Okay, so that's the basic idea, but of course, this is still scaling like order n, right? Which is, n is the brute force runtime, basically. And we're kind of spoiled now, right? We like to see square roots everywhere, so we want to see order square root n over m. And so the question is, can we get order square root n over m using Grover search? Okay. And the answer turns out to be yes. And the very, very basic idea is more or less this, but to make it work, we do have to refine it a fair bit to get exactly the runtime we want. Okay. But it's good to keep this kind of sampling experiment in mind. Okay. So this is basically how we quantize the basic idea. Okay. So exercise 13, which was in a previous section of this lecture, basically, what it showed is that, remember when we had this picture, right? And we had B, the set of unmarked items, and then we had this theta here, and psi was our start state, right? A was this guy over here. What it showed is that theta, the angle theta, was arc sine of square root, I guess here I want to use m over n in our terminology now. Okay. And basically, one can show more generally, like more generally than what we did in the previous section, that making R queries to UF, okay, so running the Grover iterate, I should say order R queries. So running the Grover iterate order R query, order R times, and I'll make this formal in a second, finds, okay, and then measuring, of course, finds a marked item with probability, and let me put this here, p equals to, and we'll see this over and over again, sine squared, and so here's R, right? That's the number of times we run the Grover iterate, and theta which is the original angle, right? Here's your theta over here. Here's your r over here, okay? And so, I mean, if you fix r, basically, you can think of, the Grover's algorithm, or running the Grover iterate r times, is just like a sampling experiment, right? Which is, it's like flipping a coin that's biased, and the odds that it lands up heads, let's say, heads meaning you found a marked item, is, whatever this is, okay? And, just, again, sanity check, let's just see if, the smaller the number of solutions you have, of course, right, the smaller the angle theta is, right, because then you're very close to B, which is the unmarked items. And then, of course, if you want, sine, remember the sine function is like this, right? So in order to get here, you need to be far away from 0, basically. So if theta is small, then r needs to be large, basically, in order for p to be large. And that's kind of what we expect in terms of the Grover iterate. Okay, in this picture, it means you would need to, if theta is small to begin with, you'd need to rotate it quite a number of times to get closer to A. Okay, so let me be a little bit more accurate. So throughout, let's now let G, and remember we defined this as, we did a reflection about B and a reflection about psi, but let's just call this G for now as the Grover iterate. And the precise formula, if you work through it, is that you'll see that G is equal to r minus 1 over 2. Sorry, this should be, it's another typo. Got to fix that. Sine of r theta, okay, over square root m. And this is basically all the plus cos of r theta square root n, sum over x in B of x. Okay, so in our earlier notation, I could really just write this as sine of r theta, basically, times A, right, plus cos of r theta times B. Okay, because A and B are unit vectors, and of course sine squared plus cos squared is 1, right, of the same angle. Okay, so, according to this formula, of course, if you do essentially order r iterations, or, r minus 1 over 2, more precisely, you'll rotate to this state. So that means that, with probability sine squared, basically, you're going to get a marked element, okay, when you measure. Okay, and sine squared r theta, and that's exactly what we claimed here, right? That's exactly what this probability was. Okay, so that's where this is coming from. Okay, so like I mentioned, kind of the beauty of this new approach of Aronson and Rall is just going to be that you can totally forget about the fact that we're even thinking about something quantum in some sense. It's just a black box sampling experiment, right? And we're just going to take that view, right, and analyze it in that way, right? Okay, so can view R runs of, well, I guess I shouldn't say R runs, right? Can view G of R minus 1 over 2, right? So doing the Grover iterate for this many steps as an abstract sampling experiment. Okay, and it's just going to be, I'm going to call the experiment E for experiment, and of course it depends on R, right? And which outputs success, let's say, or heads, if you will, if you're thinking about it as a coin, with probability P equals to sine squared R theta. Okay, so for much of the analysis, you can really just totally forget about anything quantum at this point. It's just a sampling experiment, and we're going to show how to, given access to the sampling experiment, we could actually approximately count the number of solutions. Okay, and now, of course, the question is, again, the basic idea before, right, when I started the section over here, remember we said the basic idea is that if I want to know what P is, a naive way to do this is, you try and keep doing the experiment until you get a success. And then, since the number of expected trials until success is 1 over P, then inverting kind of the number of trials it took you should, in some sense, give you an approximation to P. Okay, so our goal basically is kind of similar here. We want to approximate p because we know in our setup under the hood there's Grover search, right? We know that this formula holds, right? So if I knew p, I could certainly, if I knew p and I know r too, of course, because I'm allowed to choose r. So by varying r, if I can figure out p, then certainly I can also extract theta, which in turn tells me the number of solutions. Okay, so it's very similar to that sampling experiment we started with. And so really the question, of course, is given, let's be clear, given the ability to choose. Okay, so henceforth, for most of this discussion, I'm just going to think of, forget Grover, just think of a abstract sampling experiment. The probability the experiment accepts, let's say, given parameter r is this. Okay, that's it. So given ability to choose r in experiment ER, how many runs of this experiment? And of course, under the hood, each time we run the experiment, you're calling the oracle, r minus 1 over 2 times, because that's the exponent on Grover's iterate. How many runs of the overall experiment are needed to estimate p, right? And again, once I know p, I know r because I get to choose r, and then I can figure out theta, and that in turn tells me what number of solutions is. And the high-level outline for this, before we do anything more concrete, is going to be a bit of a fine-tuning of what we had before, right? So there'll be two main steps. And the first step, we'll get a rough estimate, basically, for theta. Okay, so we're going to try and estimate theta directly. And then we're going to fine-tune the estimate. Okay, so now what do I have? The only thing I have at my disposal, I could run the experiment E, and I can change the parameter R I plug in. Okay, and depending on that, the P changes, right? Okay, so what I'm going to do is I'm going to repeat the experiment, and I'm going to, scroll through the values of R. The naive way to do this, of course, is that you start, with R, let's say 0, and then go to 1 and 2, or something like this, right? But it turns out to be a lot smarter to increase R exponentially via an exponential or geometric progression, if you will. Okay, so I'll give you the details shortly, but for now we'll just say that we'll repeat E of R using exponentially increasing values of R. Okay, so like 1, 2, 4, 8, and so forth, until we get to the point where, when I run this experiment R, sufficiently many times, right, we'll start to see lots of marked items, whatever that means right now. Sufficiently many marked items are seen, basically. And what will come out of this is that we'll have a rough estimate of theta in terms of kind of upper and lower bounds k minus and k plus. Okay, so I'll come up with a k minus and a k plus, and those will be kind of give me some bounds on theta. Okay, and I think now's, by the way, a very good time to mention that, even if you don't know a priori, we saw that for Grover search, if you want to know the number of iterations you have to take, you almost seem to need to know the number of solutions to begin with, right? So one of the ways to get around this, if my memory serves me correctly, is that even if you don't know the number of solutions, what you can do is you can just take a geometric progression, right? So you could assume the number of solutions is 1 and run the algorithm and see if it works. And if it doesn't, then you assume it's 2, the number of solutions, and you repeat. And then you assume it's 4 and 8 and so forth. Well, you might need a more careful geometric regression, but that's the basic idea. Okay, and in doing so, eventually, you'll be within a factor of 2 of the right number of solutions, right? Because you're going up by powers of 2. And then it'll turn out that as long as you're within, a constant factor of the right number of solutions, the Grover's algorithm will still give you a marked item with the right with a good success probability, right? So you'll still find it. And the point is that since your progression is geometric, right, you don't need to make that many additional. The overhead is not so high, so you can keep the overall runtime of root n, okay, or root n over m, I guess. I don't want to get into that into any serious detail here, but let me just mention that you don't necessarily need a counting algorithm like we're using here in order to run Grover search, right? Okay, so just using this geometric progression in step 1 just reminded me of that. So let me mention it. And then what we want to do is that now I have this kind of range k minus to k plus for theta. What we're going to do is we're going to iteratively cut down this interval k minus to k plus to basically zoom in on the right value of theta. Okay. So this is the basic idea, and kind of just as a heads up, one kind of catch for this is going to be that, if I have these bounds, right, and theta is lying in between these bounds, each time what I want to do is, I either want to make k plus smaller or k minus bigger and kind of do this over and over again, each time cutting out a constant fraction of the search space. But you have to be a bit careful in the sense that, if theta, so here's maybe the real line, right, and here if you have k minus and here you have k plus, right, and if, maybe theta is very close to one of these guys, right? Maybe theta is over here. Then you really don't want to move up k minus, right? Because then you'll jump over theta, right? So you have to be careful to avoid, in this particular step, kind of skipping or jumping over theta. Okay, and so we're going to need a particular lemma that allows us to very carefully choose the value of r to avoid this. Okay. So, of course, there'll be more details about this in a second. Good. So this is the basic idea. First, we get a rough estimate, and then we kind of improve that estimate. So now let me state the algorithm and kind of well, first let me state the main claim, okay, that the algorithm is going to bias, and then we'll give the algorithm, and finally we'll analyze it. So algorithm statement. And analysis. Okay, so this is the main theorem basically of the paper of Aronson and Roll, and it states the following. So you can pick any non-zero delta epsilon that you like. Okay, so fix those. And of course, just like before, we have oracle access to UF. So just like in search. Then the claim is that there exists a quantum algorithm and what does this thing do? Number 1, it outputs not m, right, the actual number of solutions, but some estimate, m tilde. And that m tilde is going to be a multiplicative approximation, which means that it will be at least something times m and at least something times m. Okay, and the exact number will be, it will depend on this 1 plus epsilon. 1 plus 1 minus epsilon. So epsilon, remember, is this one right here, right? These are one of the parameters you can choose. So you fix your epsilon, and then, so you'll be within these bounds. Okay, so this is what we mean by a multiplicative approximation, to be formal. And it's not going to be a deterministic algorithm, right? It will have some probability of success. And that's what this delta is going to be for. Succeeds with probability at least 1 minus delta. And here's your delta, right? That's this one over here, right? That's the other parameter you chose. And now, of course, so it gives an estimate. It works pretty well in terms of probability of success. What is the cost in terms of query complexity? So it uses order square root n over m. So this is just like before in Grover search. And it should also, of course, depend on both epsilon and delta, right? Epsilon is, how good of an approximation you wanted, and delta was how often you want this thing to succeed, right? So if you want the approximation to be very good, of course, then, you know, you should pay the price, basically. So that's to be expected. Okay, and number 4, the number of qubits it uses is, you know, just like before for Grover search, it uses basically little n qubits, okay? Or something on that order, basically, I should say, because there's some classical processing on the side that takes place. Okay, but the point is that it's efficient in terms of space. Good, so that's the basic premise, right? The setup is just like before. You pick your parameters delta and epsilon. I'm going to give you an algorithm which gives you a relative approximation of this form. That is multiplicative error. It works with probably 1 minus delta. It uses essentially the same runtime as before, and you know, here we can imagine that maybe we want epsilon to be constant, for example, and delta can even be, you know, polynomial if you like, but because then you'll get polylog factors basically coming out. But even then, you know, succeeding with a constant probably is arguably good enough. Okay, so that's the statement of the algorithm. It's kind of exactly what you would hope for, given what we know about what Grover search can achieve. Okay, so now let's state the actual algorithm. Okay, so here there's going to be, before I write it down, like throughout, we're going to assume basically, so remember that when we talked about Grover search, in the analysis, we had this thing where, you know, we wanted to get up to A, right? We started at B, and we wanted to get within this cone eta, right, of A, so that we succeeded with probability half. And kind of the way we simplified the analysis is we assume that, you know, the number of solutions is not too big. It's smaller than n over 2. And that made sure that, you know, this the angle theta was not so big, right, so that we would never have to rotate past A and do more than one loop to land in this cone, right? We were always guaranteed that there's some number of iterations R so that we would land perfectly in this cone. And so we're going to play a similar trick here. We're going to assume something much a bit stronger, but it's basically good enough, right? You can assume that the angle theta, the number of solutions, is even smaller if you like. It doesn't have to be a half. Let's assume that the angle is at most pi over 1000. And one way to make this happen, basically in a very trivial way, before I said you can assume the number of solutions is not too big, because if it was, then you could just sample, for example, and solve the problem classically. Another clever way to do this is what you can do is you can take your oracle, right? And if you want just a small number of the inputs to be good, then just add a bunch of dummy inputs to the oracle that are bad, right? You just build a bigger box around your oracle. Otherwise, add dummy indices to UF. So you extend UF. So these are dummy indices x such that f of x equals 0. Okay, so you can artificially kind of push down the number of solutions. Okay, that's totally allowed. And now what I'm going to do is I'm going to state the algorithm. The algorithm is going to have a certain number of parameters in it, like, for example, the number of times you do some operation. For now, those parameters, I'm not going to put in explicit numbers. I'm just going to give them names for now. And that's just because I don't want you to be distracted by the explicit numbers that go in just yet, but rather to kind of see the algorithm at a high level for what it is. Okay, so here's the algorithm. So step 1, I'll write it in steps. So we'll start by having a counter t set to 0. Step 2 is going to be, remember we said in the high level outline, there are 2 main phases, and the first phase was to get a rough estimate for the angle theta. And this will involve basically a loop until we break out of it. The first step in the loop is, let's pick R to be the largest odd integer. Because remember, when I pass an R into E, right, it runs the Grover iterator for g to the R minus 1 all over 2. So R minus 1 should be even, so therefore R should be odd. The largest odd integer, less than or equal to, okay, so here's a parameter. I'm going to give it a name, let me make it green. C1 is just some parameter for now. It's some constant bigger than 1. Okay, I haven't defined it yet. So it's some constant bigger than 1 to the t. Okay, maybe I'll use my t over here. T is red. Okay. Okay, Okay, so the first step is we basically have a geometric progression, right? I have some number c1. Let's imagine c1 is 2 for now, right? And every time I go through the loop, t is increasing by 1, so the number of iterations basically is growing geometrically, right? So maybe it's something like 1, then 2, then 4, then 8, and so forth. That's all this is saying, okay? And then what we'll do is we will run the experiment. And remember, I'm just going to think of it as a black box sampling experiment. I'm not going to care what's under the hood right now. Here's another parameter c2. Okay, again, I'm not going to state what it is just yet. So run the experiment some number of times, recording each of the C2 items sampled. Okay, so remember, every time I run the experiment, it runs the Grover iterate under the hood r minus 1 over 2 times, if you want to be reminded of that. And of course, at the end, we measure, and so each time the experiment produces to me some item which is sampled or not. So if I run this C2 times, I get C2 items. And now if at least 1/3 of the recorded items in this previous step, X, are marked. Okay, so if a large number of the items, now I'm starting to see a lot of marked items, basically, that means that, roughly speaking, the number of iterations I'm taking, right? What is R, right? If you think back to Grover search, R is telling me kind of how much am I rotating this thing, right? So if I'm getting to the point where my choice of R is landing me close to A, I'm going to see lots of marked items, right? And so that's kind of what this is trying to capture, right? When I get to the point where I start to see lots of marked items, a constant fraction are marked, and we will make this formula, of course, it's time to break out of the loop, right? I have a good estimate for what R should be, right? It's going to be roughly C1 to the T, whatever that was. So let's define kind of like the right value of T, quote unquote, as just T. Let's call it T star, and we'll exit the loop. Okay, and otherwise, what we do is we just increment T and repeat. Okay, so this is the basic first step, and we're trying to be a little bit more clever about getting a rough estimate for R, right, the right value of R. We're doing a geometric progression, so we don't have to do this too many times. Okay, and so what you do now is that, remember I said that you'll get this kind of estimate, k minus to k plus. That's what we said in the outline. And indeed, now I'm not going to call them k minus, k plus. I'm instead going to call them theta min and theta max. Okay, so theta min, theta max is going to be the formal name we'll use now. So the thresholds are going to be on the lower end. We'll have theta min, right, which is going to be 5 over 8, if you want to be precise. Again, you're going to see this parameter c1, right? It's the same c1 as here. It follows from that, whatever that geometric factor was, to the power of T star now. T star was, the magic value of T we stopped the loop at up here, plus 1. Okay, and the upper value for the range, the upper bound for the range is going to start at almost the exact same thing. 1 over, again, C1. Again, you're going to have T star. The only difference now is that instead of having a plus 1 in the exponent, I'm going to have a minus 1. Right? And the reason why, theta max is bigger than theta min is that you should remember here that C1 is greater than 1. Right? I haven't told you what it is yet, but it's something bigger than 1. So, if it's something bigger than 1, then this thing is smaller than 1, the inverse of it. And so the bigger the exponent, the smaller the number gets, right? And here the exponent is smaller. So this number is bigger. Okay, so after the first stage of the algorithm completes, this is our estimate, basically, based on the number of iterations T in step 1 for where the true value of theta, that angle in this picture, lies. Okay. Now we're going to start phase 2. So this is kind of phase 1, if you will. And now we're going to start phase 2. And so let's just reset our counter. So let's reset T back to 0. Okay. And now we're going to have a second loop that's going to fine-tune our estimate. Okay, so loop. Okay, So what do we do in this loop? So now we have to be a bit more careful. Now we're going to very judiciously choose what r is going to be in our sampling experiment, the number of rotations basically, so that we can kind of zoom in on the right value of theta. And we have to do it, remember, in such a way that we don't actually jump over the correct value of theta, that we don't move up our boundary, either the lower end or the upper end, too quickly. And so we're going to have to use a special lemma to make sure we pick the right choice of r, which we'll state and discuss later. So in these notes, I'm going to give this lemma a name. It doesn't have a name in the original paper, right? But I like to call it the steady hands lemma to choose r. And this just kind of reminds me of those egg races where you have to hold this egg in like a spoon or something and run across the field and not drop it. And this is kind of feels like the same, right? You're trying to very carefully maintain balance and not kind of destroy theta, right? Okay, so we'll state and use that, talk about that lemma later, but for now, just assume that there's some magic lemma that tells me how to choose r in a clever way. And now I'm going to do something fairly similar to before. I'm going to run the experiment many times, right? So here, like the overall setup is roughly the same, right? You pick a choice of r according to some rule. Before, the rule was a geometric progression, okay? Now the rule is instead going to be whatever the steady hands lemma tells us. And the next thing you do is once you choose r, you just repeat the experiment many times. And then you just see if the number of successes you saw passes some threshold. Okay, so before the threshold we wanted was a third. Now it turns out we want a slightly different threshold. It's still a constant. Okay, I'm going to run ER some other parameter C3 times. Again, it doesn't matter what it is right now. Again, we'll record each of the C3 items produced. Okay. And now, just like part 2c over here, we're going to have some if a constant fraction are marked, then do something, right? So here the rule is going to be slightly different. We're going to look for half of the items being marked. So if at least half, okay, not a third. Let me write it this way so it's a bit more directly comparable to part 2c. If at least half of the items are marked, then I'm going to increase my lower bound. Okay, so then you want to increase the lower bound. And the way we'll do that is we'll set theta min, we'll update that to be the upper bound over delta. And I'll tell you what delta is in a second. For delta is defined as follows. So 0.1 plus 0.9 theta max over theta min. Okay, for our discussion at this level, don't worry about the exact value of delta. The point is, it's always something strictly bigger than 1, right? Because theta max is bigger than theta min. So this sum will always be something bigger than 1, right? So theta min, you're moving it up from below. And how far do you move it up? Well, it's whatever theta max is divided by something bigger than 1, right? So that means it'll be something smaller than theta max. Okay, so if you basically saw a majority of the items being marked, then that means that theta must have been, well, in the analysis we'll see that means theta must have been closer to the top end of the range. So you move up the bottom end, theta min. And otherwise, if you didn't see that many marked items, you saw less than half the items being marked, that means that theta was probably closer to theta min. And so we should move down theta max now. Otherwise, set theta max. And what do I want to do? I'm going to, remember delta is something bigger than 1, so I'm going to do something similar to before. I'm going to take the lower threshold theta min and multiply it by something bigger than 1. So this new quantity theta max will still be bigger than theta min. Okay, so that's how we decide to update the range we're working in each time. We'll have an exit condition now. So if the theta min and theta max are sufficiently close to each other, and sufficiently close is dictated, remember, by epsilon, which is the degree of precision I wanted, right? So if theta max is at most 1 plus epsilon over 5 theta min, Then we want to exit the loop. And otherwise, we just increment the counter t equals to t plus 1. Okay, so if we've narrowed down the range enough between theta max and theta min, we exit. Otherwise, we continue. And so that basically ends phase 2. I guess I should have drawn this thing much bigger. And in the last step, of course, we return our estimate. So what I'll do is I'll take theta max. So I have a range, right? But the range is so small that it turns out I can pick anything in the range theta min to theta max now. So let's just pick theta max. So now I don't exactly want theta, right? I wanted to estimate the probability p. So once I know theta max, I could then estimate that, right? And so it turns out the right formula to choose is this one. M tilde is our estimate to n times sine squared theta max. Okay, so that is the basic algorithm. Maybe I'll see if I could zoom out just a touch so it'll all fit on one screen. There it is, right? So 2 phases, rough estimate, right? We basically keep increasing the number of iterations, or you can think of it as you keep increasing the rotation size we're taking each time, right? So, if we're in this picture, we first guess that, we pick a rotation angle, so we either do that or then it increases geometrically or like that, right? Until we get to a point where we're sufficiently close to this that we start to see lots of marked items. That's what this one is doing. And then you kind of keep track of what R or equivalently T was at that point. That gives us an estimate on theta in terms of upper and lower bounds. Here they are. And then we want to do a very similar kind of setup where we want to kind of shrink this interval theta min to theta max in order to get a very good estimate of the right value of theta and hence of p. So let me just tell you what the other parameters are. I had 3 parameters now, C1, which define the geometric progression, C2 and C3, which told us how many times to repeat these experiments. And so, for completeness, let's state what these guys were. The one we will see again is C1, so maybe I'll do this in red. I mean, the other ones we'll see as well, but kind of the one we'll see a little bit more explicitly, let's say, in our discussion here, is C1 is not 2. Remember, it's supposed to, C1 to the t is supposed to give me a geometric progression, so it's bigger than 1, and it turns out, for example, that 12 over 11 will work here. So choose C1 equals 12 over 11. Choose C2. This is the number of times we run the first in E of R, basically, in each iteration of the loop. 10 to the 5 ln 120 over delta. Okay, delta, remember, tells us the success probability. It's linked to that. So obviously, the better success probability you want, the more trials you have to do to make sure you have a better confidence interval. And C3, likewise, is the number of samples you take in each iteration of the second loop. The ln of 100 times 0.9 t all over delta epsilon. Okay, so if you set your parameters this way, the proof will go through. So that's the basic setup of the algorithm. And now let's try and sketch the proof as to why this works. I mean, obviously we're not going to do it in full detail, but we'll try and give a sense as to why it works the way it does. Okay, so analysis sketch. Okay, so this is basically the proof of Theorem 17, which, let me just briefly remind you now that we wrote the full algorithm down. The theorem said that, you pick your delta and epsilon. I'll give you an algorithm which produces an estimate to m, up to plus or minus epsilon. Will succeed at probably at least 1 minus delta. The cost will be basically Grover's cost, multiplied by these parameters which dictate your success probability and the accuracy. And space will be order log n qubits. Okay, so here we're going to focus basically on these points here. We won't focus explicitly on space. But I think it should be fairly kind of obvious if you kind of sit down afterwards and think about it, that you also get the space claim. Okay, so what I'm going to do is I'm going to kind of break this down into so-called checkpoints. So checkpoint 1 is after the first loop terminates. Okay. So it's kind of like an invariant, if you will, in some sense, right? So remember in the first loop, we first tried to guess what the right value of R was, basically, by running this experiment ER C2 times, and then stopping as soon as we saw a third of the values being marked. So what we did after that is based on the value of T star we got, we said, okay, theta min and theta max must be this and this. That's the way we set it up, right? And so obviously the claim is going to be something along the lines of, after the first loop finishes, right, with high probability, theta is indeed going to be between these values of theta min and theta max, right? I mean, otherwise it doesn't make sense to continue in this algorithm. Okay, so after the first loop terminates, the claim is that with probability at least 1 minus delta over 2, okay, delta, remember, being that parameter. What is theta? So here's theta. So theta is, of course, going to be some threshold, and it's going to be at most 5 over 8, 12 over 11 to the T star minus 1. And remember that, what was this thing? This was nothing other than 1 over C1, right? That was that funny 12 over 11. Sorry, I should say C1, not 1 over C1, I think, right? Make sure I don't have a bug here. Why do I have 1 over C1 there? Okay, there's a typo somewhere here. Maybe one of these needs to be inverted. Oh, sorry. That's correct. That's correct. I think this should be 1 over C1. Sorry. So there's a typo in my current version of the course notes. That should be 11 over 12, not 12 over. That should be 11 over 12, I think. Okay, well, I'll have to check the paper later. Okay. So theta should be at most this, and it should be at least 5 over 8, 11 over 12, T star plus 1. Right, and intuitively, it should be 11 over 12 and not 12 over 11, because this should be bigger than this, right? So if this number is smaller than 1, a smaller exponent means that this number will be bigger, right? And a bigger exponent will drive this thing down further. So this should be the right answer. I should update the course notes. Okay, so that's the claim, that with high probability, 1 minus delta over 2, theta will indeed be in this range. Okay, good. And so how do you kind of show this claim? I mean, again, we're not going to go through all the details. There's some algebra involved, right? But the idea basically to show the claim is you want to focus on a threshold. T0 for t. And the point is that, as long as t is kind of smaller, so long as t is smaller than t0, basically, the probability that we'll see many successes will be very small. And as soon as t grows bigger than t0, then the probability we'll see many successes will now be overwhelmingly close to 1, basically. Okay? So you'll have this some sort of phase transition happening, right? And so this intuitively roughly says that what we're doing is we're flipping a coin, right? We're doing Bernoulli trials. We have a coin, this Grover iterate, this experiment E of R, that for any fixed R outputs some heads, let's say, with a certain probability, right? And if we get R just right, then we'll be very likely to see lots of successes, basically. Okay, so maybe I won't say more at this point. Let's just continue with the analysis. So we have a threshold, basically, and what do? We'll set T0 such that, as the largest integer satisfying 12 over 11 to the T0 times theta is at most 5 over 8. Okay, so of course you don't know theta ahead of time, so you also don't know T0, but the point of this is that there's some threshold which we don't know, but you remember in the first loop, we keep increasing r. And as soon as r is big enough, we're going to argue that, whatever this magic t0 was, right? Remember, r is basically tied to t0. Then the probability of seeing many marked items is going to be very large all of a sudden. Okay, so the way we define this threshold is like this. Again, this is just for the analysis. We don't know t0 beforehand. Okay, and the claim now is that, we're not going to prove this here, but, it's just a couple of lines of basic algebra with a bit of thought, right? One can show if, t is smaller than t0. So basically, if the number of trials, and, I really do want to show you that line again, just so, remember what we're doing is that, we keep increasing t, right? And based on that, we pick r to be something like c1 to the t, right? And so the claim is that so long as this t is smaller than this magic threshold t0, right, the odds of seeing many successes in line 2 are going to be small. So in particular, what we can prove is that, if t is smaller than this threshold t0, for a single trial of ER finds a marked item with probability at most. Okay, so if you run ER once in that line, I guess 2b, p equals to, remember this is the same formula as before, sine squared r theta, right? And it turns out that this can be shown to be upper bounded by 12 over 11 to 2 times 1 plus t minus t0. And here we're using the fact that t is smaller than t0, right? So this exponent here, it's an integer smaller than t0, which is also an integer. So this exponent here, what's in the brackets, will be at most 0, right? And quite possibly smaller, right? So that means that, if it's, a negative number, for example, this exponent, then you're inverting this fraction to something that's smaller than 1, right? And so it follows that this thing here is always going to be strictly smaller. Well, it's in fact smaller than 0.33, right? Which is, of course, strictly smaller than 1/3, because that's like the infinite expansion. 0.33333. Okay? And so what this means is that, here I'm going to now apply Chernoff bound, right? If in one trial I have the probability of success being smaller than 1/3, and it's off by a constant amount, then if I repeat this trial many, many times, and on average I try and see, I count the fraction of successes basically, with overwhelming probability by the Chernoff bound, I'm going to have less than 1/3 of my trials being successes. Okay, here we're really using the fact that each run of ER is completely independent, of course. Okay, so therefore, over m trials, when t is strictly smaller than this threshold t0, we expect to see strictly smaller than 1/3 of the trials being marked, or outputting a sampled, a marked element. Okay, and so slightly more formally, you would basically show, right, that you would use the Chernoff, sometimes called the Chernoff Hafting Bound. The version I have in the notes is in exercise 18, basically, and maybe I'll go through that in a second, just to remind you. So the Chernoff Hafting Bound allows you to conclude that, remember in this step, C2 is the number of trials of ER, okay? So the number of trials is C2, so if that, whatever that number was, I'll just copy it here. If we do that many trials, then the probability of incorrectly seeing too many successes, right? The probability of seeing more than 1/3 marked elements, this is going to be small, right? And it's going to be at most delta over 4. Okay, so again, delta is this accuracy parameter we have here. Why did this not go red? There you go. Yeah, delta over 4. Okay, so so that's the basic premise, and you're going to see this thing show up over and over again in this discussion, right? If for a single run of this Bernoulli trial, you have probability strictly smaller than, some threshold C of succeeding, then, when I run this many, many times, then the fraction of successes I see will be strictly smaller than C with overwhelming probability. And the way you formalize this, and let me just write this down, I'll let you play with it as an exercise, but if you haven't seen it before, the Hafting Bound, I don't quite remember if we covered it in this course already. It's been a long semester, right? It states the following, right? It says, and I'll give you a slightly simpler version of it. So suppose you have independent, this is very important, random variables, okay, RVs. And I'm going to assume that each of these guys, the values they take is between 0 and 1. But let me be clear, you can generalize the statement to account for arbitrary thresholds. But they just need to be bounded with some bounds that you know ahead of time. And their arithmetic mean is supposed to be, let's just define it as x bar of, just add them. And then you take their average, right? Okay, so then the Hafting Bound states the following, that if I run an experiment in which I literally just sample x1 through xn, I repeat this many, many times, n times, I draw many samples, and then I take the average, right? x1, I add them all up, and I take the average in this sense. So here's this thing, right? That's my experiment. Repeat experiments and take the average, right? How far is that going to be from the genuine expectation of this quantity, right? So remember, E is just the expected value of this thing, right? Remember, of course, x1 through xn are random variables, so of course x bar is also a random variable. So there's some ideal expectation for this versus something I'm getting in my experiments, right? So how big is that deviation, right? And the claim is that if that deviation is, well, the probability of that deviation being large, let's say at most t, it's a very good bound, meaning you're going to get 2 times e to the minus 2, and let me put n here, and n is, n is the number of trials, right? Here it is, here's n. So as the number of trials you do grows, right, the probability of failure basically drops off exponentially. That's very, very good. And the other thing I used was t, right? So the further you get from the true expectation in your bound here, right, again, it drops off exponentially. Okay? So, this is the kind of bound you can use to formalize this argument that, if your probability of success is strictly smaller than a third each time, you're off by a constant factor, then, when you do this many, many times, like you have many trials like this, and then you take an average, basically you want to know what's the fraction of successes. You do something like this, right? The odds that you're going to deviate from the true expectation, right, are going to be extremely small. Okay, so I highly, highly encourage you to use this, to do exercise 18, basically, in the notes. Okay, so what did we say? We basically said that, there's this magic threshold t0, so that if the number of trials is smaller than t0 in the first loop, then you're very unlikely, basically, to see a third of the elements being marked. And so you'll increment t by 1 and you'll repeat the loop. And now here's the other case. Conversely, if, t is larger than t naught, so in particular, if t is at least t0 plus 1, let's say, it turns out that you can show something similar, basically the same idea. Like I said, we're going to see this argument over and over again. P is now going to be bounded away from a third from above. All right. So again, same thing, this Chernoff or Hafting bound can be used to say that with probability at least 1 minus, and so here's your delta again, over 4, a third of the samples are marked. Okay. Okay, so and with that, we can then conclude the bounds that we wanted, basically. This is just, again, a proof sketch, of course, that indeed, when we exit the first loop, basically, what we have what we want. Here's that magic t star, basically. when t star kind of approaches that threshold, t naught basically, you're going to be guaranteed that these bounds basically hold, because all of a sudden you'll be overwhelmingly likely to see a third fraction of the samples being marked, basically. Okay. Checkpoint 2. And as you might guess, this is after the second loop terminates. Okay. So let me just remind you what the second loop looks like. Here it is, right? So now, I've set my thresholds, theta min, theta max, and I'm going to do roughly the same kind of idea as before, meaning I'm going to use some sort of rule to pick the number of iterations r. I'm going to run the experiment ER a certain number of times. And now, if I see at least half the items marked, I'm going to move up the lower bound. And otherwise, if I see very few marked items, I'm going to move down the upper bound. Okay. And my exit condition is precisely this thing, right? As soon as these guys are, within the right ratio of one another, I'm just going to exit. I can check that, right? And now, of course, so of course when I exit, I know immediately, by definition, what I've written here, I know that the ratio between theta max and theta min is at most 1 plus epsilon over 5, right? Okay, so as stated, we know that after checkpoint 2, right? Here's checkpoint 2, right? After the second loop terminates, we know that as soon as we reach line 6, remember the exit condition for loop 2, as we just stated, ensures, right, that the ratio between theta max and theta min is, something small and dependent on the desired precision epsilon we put into the algorithm, right? So this we know for sure, assuming the loop exits, right? And indeed, once you have this, right, we can conclude something nice, which is that because theta min and theta max are so close together in this multiplicative or relative sense, right, now I can choose any theta tilde in the range from theta min to theta max. They're so close it doesn't matter. And any such theta tilde will satisfy these bounds, okay, upper and lower bounds on the true value of theta, okay? And, I'll let you do this. It's the next exercise in the course notes. I'll let you argue that, once we have this, then we can argue that the estimate output by the algorithm, basically in the very last line of the algorithm, will indeed satisfy the bounds on M that we wanted in, I believe it was the first claim of the statement of the theorem for the algorithm. Okay, so assuming that loop terminates, we're in good shape. We're in good hands, things are close, and we can kind of just spit out the answer. The only question is, how do we know, of course, that the second loop will terminate, right? And for this, we know you have to dig into a bit of the details, but, let me just kind of sketch how this goes, right? The basic idea is that, once we hit line 3, right, after the first loop terminates, we know exactly what theta min and theta max are. We've given them explicit values, right? And so, the definition of this capital delta, which was deciding how we updated the thresholds in the second loop, this was just, this definition, I'm just rewriting it here, is 0.1 plus 0.9 plus this ratio, right? And so when we enter that second loop, basically, for the first time, this ratio, when you work it out, you'll see it's about 1.19, right? And the point here is that it's some constant bigger than 1. So that means that if this is bigger than 1, then, 0.1 plus 0.9 times that thing will also be some constant bigger than 1, right? So remember, every time we went through the loop, what we did is that we take our thresholds, and either we take the top threshold and we divide it by some constant bigger than 1 to bring it down, or, I think the case are slightly backwards, but basically the point is that, we always kind of move the thresholds by dividing through by delta or multiplying through by delta, right? And delta here is now some constant bigger than 1. Okay, so what this basically tells us is that every time we run loop 2, basically, we're cutting down a constant fraction of the search space, this thing right here, okay? So, eventually we're guaranteed, more or less, that this thing should, exit with certainty, right? So there shouldn't be really any error there. The only problem is that, I'm cutting off a significant part of the search space each time, right? If it's going to be a constant fraction, let's say, there is a danger, right? And the danger is this one, right? How do I ensure that something like this doesn't happen, right? So maybe, for example, here's theta max over here, right? And here's theta min over here, right? my current values, and maybe it turns out that the true value of theta, right, is very, very close to theta max, right? And how do I know that I won't accidentally pick as my new upper bound theta max this one over here, right? That just jumps right over theta, right? I mean, totally skips it. And then, sure, the loop will terminate, right? But the final estimate I'll get, you know, the small range of theta min and theta max, of course, will no longer contain theta, and so it's going to be a bad estimate. Okay, so that's where the remaining error in the algorithm is going to come from, basically, right? So we have to account for the fact that there's some probability now that we might accidentally jump over theta. But luckily, so that's this problem over here, right? But luckily there is a solution, right, to ensure that, you know, the odds of this happening are very low. Okay, and that is going to be this so-called steady hands lemma, which we'll now state and sketch a proof of. Okay, and what this says is the following. So it's basically tailored to our situation, right? So you assume that you have theta, and as kind of a loop invariant, if you will, theta is between theta min and theta max. Okay, so we know this to begin with. And remember that, you know, we started by assuming that, you know, the true value of theta is never more than pi over 1,000, right? So we have this upper bound. And, you know, after we finished the first execution of the first for loop, remember we've set these thresholds to start with theta max, theta min, and they were, you know, sufficiently close that we can now go to phase 2, basically, right? And in particular, the other assumption needed by this lemma is that, you know, these guys should be at most, say, 5 over 4, okay? This thing says there exists now, so, you know, assuming we finish the first loop, these invariants will hold. Now we enter the second loop, so there exists an odd integer r such that running the experiment E of r, at least, so here's a number, I'll just write it down, and maybe you don't need to worry too much about this particular number right now. So, but if you run, you know, the experiment this many times at least, right, and then you choose to update theta min and theta max, basically according to the rules in the second loop that we had. So I'll rewrite those now. So updating theta min and theta max as follows. So I'm going to write this in a second. Preserves, right? This is the loop invariant we're trying to preserve, right? That theta is always in this range. We never lose theta. And this happens what? Well, with probability at least 1 minus delta, right? So what are the rules now? So if the majority of samples are marked, that means we move up the lower bound. So theta max over delta. Okay, and otherwise, if they're not marked, then we move up the lower bound. Sorry, I should say, I think I said it backwards, didn't I? If many of the samples are marked, sorry, you're closer to theta max, and therefore you move up the lower bound. And if many of the samples are not marked, then you must be closer to theta min, so therefore you take your theta min and you scale it up by something bigger than 1 to get your new theta max. Okay? And there's one other thing, which is important if you want to think about the cost of this in terms of queries, right? How big is R, right? I mean, you don't want R to be too big, otherwise it will blow your cost estimate. And it turns out that, sorry, I should be a bit more careful here. This is like big theta notation, right? This is not the theta I'm using for the angle, right? So it turns out that the number of rotations R is just 1 over theta, basically the theta we're looking for. Remember, i.e. R controls the number of Grover iterates in E of R. Okay, so not only does this R exist, that makes sure that we, with high probability, we don't kind of skip over theta, but in fact that R is kind of manageable. It's not too big. Okay, so this is the steady hands lemma basically, and this is basically what we're using. So let's just quickly go over it again. if the preconditions of loop 2 hold, meaning that theta is between these bounds, basically, the bounds themselves are not too far apart, then so long as in the second loop, the number of trials you do is sufficiently large, then the update rules we had will basically preserve the loop invariant, which is theta min is smaller than theta, which is smaller than theta max. The rules for updates were just if you see majority samples marked, you update theta min. Otherwise, if most samples are unmarked, you update theta max. That's what this lemma says. And let me just show you the algorithm again, just to remind you how that gets used. Here we are. All right, so in the second loop, remember, here, every time we run the loop, how do I choose R for the experiment ER? Well, I do it using that steady hands lemma to make sure I don't skip over theta. Okay, and then I do my trials, and then I do my majority vote, and then I update theta min or theta max. I stop if they get too close of one another. Well, too close is a good thing in the sense that the precision I wanted has been achieved. Okay, so let's go down. So here's the lemma, right? And now let me sketch kind of why this lemma should hold, basically, yeah? But again, we won't do a formal proof. Okay, so the very rough idea, right? I mean, again, I'm not going to go through this given the time, but the very rough idea is the following. Okay, so you want to select R, right? And the exact value of R, it's in the course notes. I'm not going to state it here. I'm more going to tell you about, there's a formula for R, by the way. You can just write it down. But for now, for our discussion, I'm just going to pick an R, and I'm going to tell you about its, I'm not going to tell you explicitly what R is. I'm going to tell you about the properties of it that we care about. Okay? You can, again, reference the course notes to see what the exact value of R is. So the rough idea is you want to select an R which satisfies the following. Okay, so I know theta min, and I know theta max, right? Those are my thresholds. And, if I go around the circle, right, the angle, if I go around the circle, sorry, if I do like, let's say R applications, let's say of Grover search, remember that the probability that this thing, the Grover iterate, if you do it R times, basically R minus 1 over 2 more accurately, the probability that you see a marked item was something like P equals to sine squared of R theta, I think, right? And so, if I apply, if I run the experiment ER now, basically, what it's going to do is it's going to put, R in front of each of these, right? And so, these things were a certain distance apart. And what it's going to do is it's going to essentially exaggerate the distance. It's going to blow up that distance between them, right? Additively. Of course, the ratio of the two doesn't change, right? If you divide R theta min by R theta max, that doesn't change, right? But additively, the difference grows. And so we can make it in terms of additive difference. You can choose a very careful choice of R so that this thing is approximately, some quantity. The exact quantity doesn't matter for our discussion at the level of detail we're doing it here, but let me write it. Okay, so the point is that, we can choose R so that this is correct. Okay, and what is this thing? This thing is going to be R times theta min, right? So that's just this thing, right? Plus basically 90 degrees. Okay, so one angle is basically somewhere here, and the other one's like 90 degrees off, right? So we're really kind of separating them until, the additive difference, if you will, is 90 degrees. Okay? And not only that, but we can say something even a bit stronger, right? And so roughly speaking, one can show basically that this thing is going to be approximately equal to the state B, in the sense that, angle, it's going to be, some constant k times 2 pi, right? So if I do R times theta min, it's going to wrap around the circle many times, and it's approximately going to land, smack on B, that x-axis, right? B coming from, our picture of Grover search, right? Where we had unmarked items, marked items, right? So if I do this, many times, whatever R theta min is, it's going to be approximately, that angle will be approximately, B, essentially, okay? And this thing here will be, approximately A. Okay, so it'll be, approximately something like angle K 2 pi. I don't remember if it's the same K or not, but, you're off by pi over 2. right? So it'll be something like, I don't know, something like this, right? So this would be like, okay, r theta max. Okay. Okay, so what does this mean? Right, because theta min and theta max were separated, and then I could kind of blow up the additive separation between them in such a way that one aligns, theta min ends up aligning with B and theta max ends up aligning with A, right? Well, we have the following, right? So since we know as a precondition to the lemma, to this steady hands lemma, we know that we have this range, right? Theta is between theta min and theta max. So you have two cases, right? So if theta, the true value of theta is approximately theta min, right? To begin with. So if remember, the steady hands lemma is trying to avoid those cases, right? Where you have theta min, theta max. And I want to make sure that, if I run for whatever choice of r I choose in this lemma, I'm never going to move theta min inwards. I'm always going to update theta max downwards, right? So this is saying that if I really do have this situation where theta is very close to theta min, let's say, after r iterations for this choice of r we've made, right? So this is not some arbitrary r. After r iterations, we know that r theta, right here, it's in this picture, right? R theta is approximately equal to r theta min, right? So remember, this just follows because I'm assuming right here, right? I'm assuming on the left here that r theta and theta min are roughly the same. So roughly those two will remain the same, and together they'll be close to basically an angle of 0 radians, of course mod 2 pi basically. So we don't care about rotations around the circle. Okay, and so what this means is that therefore, if I now measure, right, when I choose for this value of r, right, if I now measure, then we're going to be very likely to sample unmarked items, right? Because we're very, very close to B, right? And, same thing is true if we said, same discussion, but now let's say theta was at the top end of the range, near theta max, let's say. Then same idea after, I don't like this r here, after r iterations, r theta is now going to be approximately r theta max. And now this should be approximately, like pi over 2, let's say mod 2 pi, right? And so now you're going to be, essentially aligned with A or very close to A, so you're going to be likely to see a marked item. So likely sample marked items. Okay. Okay, and so the basic idea now is just like before, and I'll give you the precise bounds in a second. But if in each run, basically for this choice of r, if you're close to a threshold, basically you'll be kind of very likely or very unlikely to see marked items. So if you repeat this many times and take an average, the Chernoff bound again will tell you that you'll be very likely to correctly identify when you're close to a threshold. So apply a Chernoff bound. Okay. So let me be slightly more formal now. That's just kind of the rough idea of, there's some magic choice of r, which I won't write down here, but there is some choice of r basically that basically satisfies this, that takes, whatever angle these two had together, theta min and theta max, and if you multiply them both by r, wrap them both around the unit circle many, many times, but it'll kind of blow up their difference additively until they kind of align with B and A, okay? And then so if you are close to one of those two thresholds to begin with, that means that you will either be very likely or very unlikely to see marked items. And you can detect that, of course, by running this experiment many, many times. So slightly more formally, let me just state kind of the bounds you would get when theta is either close to theta min or theta max. So formally, again, I won't prove this, but the idea is that if theta is kind of far away from, so this is the theta max over delta. So if you're really kind of far away from the top radius, right? the top threshold. So this is basically case 1 of the steady hands lemma. You can show that E of R outputs a marked item with probability P is equals to, remember, sine squared R theta. So again, that's where this R theta is coming from, of course, or is ending up. And it's basically a constant strictly smaller than a half. Okay? And if, on the other hand, if theta now is not bounded away from the top, but now it's bounded away from the bottom, right? So you have, this is at most delta theta min, right? And then theta max like this. So if you're kind of closer to theta max, if you will, than theta min. And of course, this is case 2 of the lemma. Then E of R outputs a marked item with probability P equals to sine squared, same thing. And now you get at least 0.6. It's actually a bit bigger, but let's just use 0.6 for now, which is strictly a constant bounded away from a half. Okay? And remember what the name of the game was, for this choice of R, I'm going to run the experiment many times, and I'm going to basically, if I see, and then I look at whether the majority of runs are marked or not, right? If in this case, Chernoff bounds tell me now with extremely high probability, the majority of runs I do will not be marked because the probability of a single marked item is bounded below a half. And so in that case, I conclude that I must be in this case, which means I'm really kind of far away from theta max. And so that's why in this case, I'm going to update theta max. I'm going to bring the top end down. And in the second case, if you're really far away from theta min, then the probability of success per run is a half, strictly larger than a half. So if you repeat it many times and look at the majority vote, then you're going to be, with very high success probability, you're going to conclude that indeed, you must fall into this case and not this one, right? So you're far away from theta min, and therefore we can update theta min in this way. So apply, let's see, many runs of E of R plus the Hafting bound or the Chernoff bound to, let me give these names, to distinguish star and double star. Okay, so again, the central kind of theme that you see over and over in this paper is that you have some sort of sampling experiment with some success probability P, and we think of these as being Bernoulli trials, right? You flip that coin over again with lines heads with probability P. They're all independent coin flips, of course, and so you're going to be very if that thing is lower than some threshold, basically, then the Chernoff bound tells you that most of the coin flips you'll see will be tails, for example. Okay. Good. So that's roughly speaking, the idea behind the steady hands lemma and how you can detect basically when theta is close to one of the thresholds. You basically kind of pick an R that's clever enough to blow up the thresholds to kind of stretch them so that they kind of sit on B and A. And then just by checking if something is marked or unmarked, right, on average, you can tell whether or not you are close to one of those thresholds. Good. So the last thing left is just to tell you what is the overall query complexity. Again, I'm just going to give you high-level statements. We're not going to go into any details. And in fact, I'm going to get you to do it yourself via exercises. So what is the number of queries the oracle in particular will need? Okay, so exercise 21, there are two parts to this, right? There's the first loop and the second loop, right? And that's where the Grover iterator is being called every time we call E of R, right? Remember, so every time I call E of R, that means you're, remember, running, g to the, I think it was r minus 1 over 2, right? So that's the number of calls to the Grover iterate, and hence to the oracle, right? So r minus 1 over 2 oracle calls. Okay. So the first loop, with very high probability, right? We argued that there was this funny threshold t0 that as soon as the number of runs t is bigger than that threshold, or sorry, as soon as the exponent in that geometric progression t is bigger than t naught, then you're extremely likely to exit the loop, right? So with very high probability, the first loop runs basically, whatever that threshold was plus 1, right? As soon as you pass that threshold, you're going to stop. And t0 was that threshold we had. Okay. And basically in this exercise, what did we want to say? So each run of the loop uses 10 to the 5, the ln of 120 over delta calls to the oracle. Well, okay, that's not entirely true. I should update that, right? Because that's the number of calls you should be making to ER, I think, right? Should update that. Okay, and then you want to show, that the number of queries in loop 1 is what? It's going to be order 1 over theta, right? Theta is the angle we start with, right? 1 over delta. Delta is going to be the parameter I get to choose for the probability of success. And of course, we don't want to write this in terms of theta. Remember, theta is really just square root n over m. Okay, so this is the cost of the first phase, and it's pretty good. I mean, there's no epsilon here, right? At this stage, you'll notice how it doesn't, there's nothing about the final accuracy epsilon just yet. Okay. And then, so I'll leave that as an exercise to prove, you'll need a few facts, but basically speaking, it's just, work through the algebra basically till you get it. And for the second loop, again, I'm not going to go through the argument, but similarly, one can show that the second loop uses how many queries? Well, it's going to be order almost the same thing, except now I'm not just going to have a theta, but I'm going to have the epsilon coming in, because now I'm really trying to zoom in on the right value of p, basically, and hence of theta, right? So epsilon has to come into play now. That was my accuracy parameter. Okay. And of course, if you just run through the same kind of translation, you'll get this. Right, so the theta is kind of what's missing up here, and it's present down here. And so this is, since the second loop has a bigger runtime, it's the same thing as the first one, but it also has the 1 over epsilon term asymptotically, then this is going to be the overall query cost. Okay, and this is exactly what we stated. Okay, so let me just very briefly just show you that theorem again, just to kind of recap. Okay, here it is. Okay, so remember, you get to pick delta and epsilon, and basically we're going to give you an estimate to m up to plus and minus epsilon, multiplicative error, success probability of 1 minus delta, and this is basically what we just saw. The query complexity is square root n over m times parameters that depend on epsilon and delta. Okay, good. So that is basically going to be our lecture on Grover search, basically, and approximate counting. Again, if you're interested, I certainly recommend you look up alternate sources. Like, for example, even Nielsen and Chuang will talk about how to do approximate counting using kind of this more classic idea used in terms of phase estimation. That's also worth seeing. But, I really wanted to cover something kind of very recent and kind of very slick, right? It's, again, there's a sense in which you just kind of use Grover as a black box, right? And think of it as a sampling experiment, and then use just kind of amplification techniques to really zoom in on the value of theta you want. So that's kind of neat. Good. So in this lecture, we saw Grover search, we saw quantum approximate counting, and that's it, I think. So hope you guys have a good week.